This presentation is basic installation and operation of electromagnetic flow meters. I'm Cliff McEwen. I'm a customer service engineer for ABB Warminster. Let's start this presentation by discussing the construction of flow sensors. The major components of a flow meter are the process connection. This is the flange, and it determines pretty much the pressure rating of the meter. The outer flow tube is either welded onto the flanges or it's casted as an integral part. The sensor coil housing not only protects the sensor coils from the environments, but also the electrodes. The sensor head contains sensor electronics and user connections. The meter tube lining, this insulates the flow stream from the sensor body, the metal parts. The magnet coils, of course, these are what set up the magnetic field. The signal sensing electrodes, there's two of them, one at the 3 and one at the 9 o'clock position. And some meters have a ground electrode. Now let's take a look at a flow meter assembly and its components. We start off with a tube and a liner. The magnet coils, these are wound on precision spools. The mounting shoe and the guides, these position and hold the coils in place. And there's a signal electrode, which is usually on this meter built inside of protective casing. There's the ground electrode. It's basically just another electrode, but it's at the bottom of the meter at the 6 o'clock position. And then we have the magnetic circuit, and this is, we'll discuss a little more in a minute here in the upcoming slides. And then the sensor housing. This is a clamshell design, which are bolted together and sealed so that the water doesn't intrude into the internal parts. Let's take a look at a flow tube, the basic components, the magnet coil, the spool, the stainless steel tube, the flow signal electrode, and the liner. Without an iron circuit, if we were to excite the coils, it would set up an unevenly distributed magnetic field across the flow tube. If we were to add an iron circuit, mild steel, the magnetic force lines would be more evenly distributed across the flow tube, allowing for a much cleaner signal. The amount of signal voltage at the electrode surface will vary depending on the distance from the electrode of the fluid particle. And you can see by these color bands that further away it gets in distance, the weaker that signal. But if we look at the influence of the magnetic field that's generated on a fluid particle, we see that it also has an influence that the further away from the magnet it gets, the weaker that influence. So if we were to superimpose these, you can see that overall we have a much more evenly distributed field, and the signal weighting is more consistent. This helps eliminate disturbances from tapers, bends, valves, and just general turbulence. We have to remember that the calibration accuracy of an electromagnetic flow meter is dependent on the cross-sectional area of the flow tube, the column of water flowing through it, and the time it takes to go through that flow tube. If the pipe is not completely full, you inherently generate an error, and that error can be as much as 50% of the flow tube. If the electrodes are at the 3 and 9 o'clock position and they're covered by water and almost 50% of the pipe is empty, you would have a substantial error on the meter, and the meter would not know that it's not totally full. This is where the installer has to make sure, or not necessarily installer, but the designer has to ensure that the meter is installed such that it is constantly full and there is no possibility that you would have an air pocket trapped in the upper portion of the meter. And in this example, you can see that we do recommend in a situation like this that the meter not be at the high point of flow, but rather you could put it in the vertical position of the upward flow. We're always talking about the flow profile and turbulence. Mag meters for accuracy require a laminar flow profile, and that essentially is a profile where the maximum velocity is in the center of the pipe and it diminishes to zero as you get to the outside of the pipe. We can take a look and see what happens to that laminar flow profile when you introduce a flow from an elbow or a T-section. If we take a standard flow profile and then we introduce a flow from a T, you can see that as it rounds the corner, the velocity at the upper part of the pipe here is going to be greater than the middle of the pipe. And in the lower portion of the pipe, you can actually see that the flow profile is reversing. This reversing actually causes a swirl in the meter. And this is probably one of the biggest problems people have when they put a flow meter on an elbow in the wrong position without enough upstream diameter to dissipate that swirl. Let's take a look at a couple of instances where we're going to put an elbow on the upstream side of the pipe at X diameters upstream. It's a 90-degree elbow. So let's start at the zero position. It could be either 0 or 180 out coming the other way. Or you can put it in at 45 degree or any angle in between. Or come in from the 90 degree or flip it completely over and come up into the pipe. As you can see, the 90 degree coming into the pipe at 90 degrees gives you your best performance, usually around 3 to 5 pipe diameters upstream. You can see as you start approaching 0 degrees, that is rotating that elbow to the side, the inaccuracy, the error is greatly increased, even as far out as 10 to 15 pipe diameters. Let's take a look at a situation now where we put a straight run between two elbows coming in, they're 90 degree elbows, coming in at the 0 degrees, 45 degrees, and the 90 degree positions. You can see here that we have a whole new set of errors, and again, it doesn't really help you a whole lot. The 45 degrees seems to be the lesser of evils here. It's predictable to a degree, but yet very unpredictable. And again, your best bet is to try and get as much upstream separation or straight run as possible. Separating the two 90 degree bends by a 2 pipe diameter straight run doesn't improve the situation anymore. In fact, it makes it worse. Here you can see that your 0 degree and your 90 degree are just literally folding away from each other. Now this really starts to get crazy when you bring double 90 degrees in on different planes. And again, you're starting to mix 0 degrees, 45 degrees, 90 degrees. It literally wreaks havoc on the meter as far as turbulence going into the flow tube. And again, this is why we try and grab as much straight run as possible to stabilize that flow before it gets into the meter and of course across the electrodes. And as you can see here, the error is just kind of crazy as far out as 25 pipe diameters. It does start to stabilize. I think the blue line represents the 90 degree coming in from the 0 position, but it just kind of validates the fact that it's not a real good idea, and if you're going to do it and you expect performance, you're really going to have to get some straight run upstream. Let's talk about mounting valves. If you put a control valve, an isolation valve on the line, ideally you want to mount it downstream. It doesn't interfere with the flow profile going into the mag meter, and we always look for something greater than 2 pipe diameters downstream, just to prevent any counter turbulence from backing up into the meter, which can happen. By the way, we want to emphasize the flow arrow here. If you have bidirectional flow, all bets are off on this one. Here we have a control valve mounted upstream, and this is the shocker. This usually gives people sticker shock when they see that. We kind of recommend for a valve, like a ball valve or a partially gate valve, actuator or motor actuated valve, 10 pipe diameters upstream. Again, any obstruction in the flow stream is just going to cause turbulence and introduce that swirl into the stream. I threw this slide in here to make people feel better that if you have isolation valves, I don't know why anybody would want to do this, to completely isolate the meter, maybe so they can maintenance the meter. If you put gate valves in there, if you've got them lined up and well gasketed, gaskets fitting properly, not into the flow stream, and the gate valves are completely open, it's just like going through one pipe into the meter out of another pipe. The only thing you got to do here, we'll talk about bonding, is bonding would be very critical in a situation like this. And when we say bonding, we're talking electrical bonding. As a rule of thumb, putting reducers at the inlet and the outlet of a mag meter really doesn't affect it, as long as they are concentric tapers and not eccentric tapers. If you have an eccentric taper, you're automatically going to change the velocity on one side of the taper as opposed to the other, and that will in fact cause turbulence and inaccuracy in your readings. Some of our data sheets contain, or some of our tech bulletins contains this table, and it shows the relative type of sensor and inlet outlet upstream pipe diameters. You'll see the Aquamaster here is a 0 downstream pipe diameter, both on the upstream and downstream side. And there's a caveat here. Notice that the elbows come in from above or below, and that is so that it does not generate that swirl turbulence from coming in from the side. AquaProbe is a whole new animal. It's an insertion type meter, and they are very sensitive to turbulence and disturbed flow. So the general consensus here is on the inlet side, flow going from the inlet to the outlet, you're going to want to have 25 pipe diameters upstream and 5 pipe diameters downstream. And they don't play nice. Process master, you can pretty much, as you saw in some of the previous graphs, get away with 3 pipe diameters upstream and 2 downstream. The FSM 4000 again follows that same principle, 3 up, 2 down. And water master, you can have 3 pipe diameters upstream, and you'll see that we have the hexagonal or the reduced bore, and 0 downstream has a tendency to smooth the flow out and prevent turbulence. And if you want the higher accuracy, you got to have that 5 pipe diameters upstream. And as a parting note on this, it just makes common sense that the more upstream straight run that you have, the smoother and the more laminar your flow profile will be. Now we're going to start into the part of installing a flow meter that is the great mystery, and that is the fluid contact rings and grounding plates, and this will segue into bonding of the meter. The function of a ground ring or a fluid contact ring is to complete the measuring circuit through the flow meter from the electrode through the flow stream to the meter body. That's its function. That's its only function. If you put them in there and use them as a metal gasket and don't hook them up, and you call us up and you say, my meter is reading all over the place, first thing we're going to tell you to do is connect your ground ring to your meter body. Step 1. Now, ground rings come in a variety of types. You'll see that we have a ground protection plate. Now, that's a protection plate that serves two purposes. One, it is a ground or fluid contact ring, but it also protects the liner, and you'll see that it's mounted on the meter. You don't have to take the screws out, and you don't have to remove it. Gasketing is metal to metal. Whenever you have a metal to metal contact, you have to gasket to seal it. Metal to metal does not seal well. Or you have your insertion ground rings. You also have your PTFE for the chemical industry. That's a conductive PTFE, and they're used. I mean, they're expensive, obviously, but they're kind of a specialty items for processes where you can't use metals like cast alloy C or stainless steel. In battery-powered meters, our Aquamaster, grounding rings are essential. They are a low-power driven device, and you want to make the signal as clean as possible. So you really do have to have these installed, and you have to have the meter bonded properly. And we're going to move on to the next set of slides, which we're going to go into bonding in detail. But before we move into bonding, we're going to talk about something that's starting to pop up a lot in the water industry, and that is impressed cathodic protection. And it's an even bigger mystery than ground rings. Impressed cathodic protection imposes a current or a potential on the metal pipe to reverse or nullify the galvanic corrosion effects. Whenever you put a metal pipe in the presence of a conductive fluid in the earth, which happens to have minerals in it, the pipes corrode. They coat the pipes with petroleum-based products, and now we're starting to see these impressed systems where they have these big electric generators. The pipes are electrically connected to each other, and they run a 50-volt signal as much as 50 amperes through it. And the idea is it's just like a battery. If you reverse the polarity of a battery, you're not going to kill the battery and diminish the metal product in it to generate the voltage, but instead what you're going to do is prevent that electrolytic action from happening. This represents a problem to mag meters because mag meters sense voltage. And here we can see we're putting voltage into the pipe, which is in the conductive flow stream, which comes through the meter and swamps the meter out, and in our meters it'll shut it down. It's just something that needs to be brought up, and if you do an impressed cathodic protection system, it's an installation that has to be done by professionals. The meter function has to be understood, and you have to handle it with kid gloves. When you install a meter for cathodic protection, you have to completely insulate. The key word there, insulate the meter body from the pipes that it connects to. Now this requires insulating washers, or gaskets, on both sides of the fluid contact ring. The bolts have to be put through insulating sleeves through the flanges. The heads of the bolts have to be insulated by insulating washers, and the nuts have to be insulated using insulated washers. And you don't connect the meter or the meter body to the connecting pipes. It's a tricky thing that has to be done, and we've had several cases that people have run into problems because they don't quite understand how all this goes together, and it is an expensive prospect just to put the meter in. It's not your basic nuts and bolts kit. You basically got to go out of your way to make sure that this thing is electrically insulated from the pipes on both sides. Another addition to this, and it's not in this presentation, but in battery-powered meters such as the Aquamaster, the sensitivity of the meter and the low voltage capabilities of the electrode require recommend, I'll just say recommend 50 pipe diameters upstream of insulation. In other words, what you connect to the meter, you should have 50 pipe diameters of insulation. So the spool piece in some installs that I saw were plastic, literally, connecting to the meter to prevent the impressed voltage from getting to the meter, swamping it out and destroying the signal. Well, here's another mystery of installation, and that's the torque value. People call us up and they say, I got this mag meter, what do I torque it to? In the old days, yeah, we did supply torque, but we also supplied the bolts, the nuts, the lubricant, and the gasket. Nowadays, we just simply sell a meter because, of course, for price reduction, they eliminate all that. People want to supply it themselves. In order to know how much torque to put on a system, you have to know, one, the process pressure. You got to know how much pressure is going to run through it. If you don't torque it enough, you'll blow the gasket out. You also have to know the gasket specifications. You have to compress a gasket so much for the operating pressure you're going to operate at. And that's given to you by the manufacturer who made the gasket that you're going to use. The number of bolts in a flange, well, yeah, we can count those. The flange rating. Flange rating will give you the maximum torque you can put on the unit. If you exceed the maximum torque that the flange is rated for, which you can find out in the ASME specifications, you'll warp the flange. Yeah, you can warp that flange. And the bolt specifications, you have to take that into consideration too, because you can actually put so much torque on a bolt, you can snap it or stretch it, just like a rubber band. Now, it's not all that difficult. You can go through tons of calculations and just make yourself crazy. There are plenty of sites online where you can throw all your parameters into and they'll calculate the torque for you. But there's always been this cute little formula that's been hanging around for years, and this is straight out of mechanical engineering manuals, something I learned at Drexel. You can estimate torque, and it's very accurate for the most part. And this little equation, T equals 0.0167 times F times D. T is your torque in foot-pounds. K is a dimensionless nut factor, and that's what the 0.0167 is. I'll explain that in a minute. F is the axial force in pounds. That's how much force or stress you're putting on the gasket. And D is the nominal bolt diameter in inches. Now, you're saying, okay, well, where'd you get the force in pounds? Well, I'll show you that in the next slide. But the dimensionless nut factor, that's an interesting one. You can go through all kinds of calculations for a well lubricated or so much friction coefficient, rusty fasteners, blah blah blah, dit. Generally it falls between 0.01 and 0.025. You kind of slice it down the middle and you say 0.0167. That's a nice even middle of the road value. Using that equation and then using some information about your gasket and the diameter of your bolt, you can figure out how much torque to put on any meter, or flange for that matter. Let's take a look at an example of how we used to do it back in the old days when we actually printed this data in the manuals. This is an example I put together for an 8-inch meter that made the torque estimates. All the bolts are new, and the material selection is in accordance with EN 1515-1 Table 2, which is a spec for galvanized bolts. The gasket is a homogeneous rubber with a Sure diameter A, not to exceed 75. That's a typical rubber gasket. All the bolts are galvanized and adequately lubricated. It means you pretty much slap the grease on there when you're tightening this thing up. All the threads, not some of the threads. The values are calculated using carbon steel flanges. Okay, that's straight out of, B16.5. The flow meter and mating flanges have to be correctly aligned. You can't have things hanging out in midair and some stuff doing the cantilever thing. Now you're given the pressure, the operating pressure of the system you're working on, and I chose 300, 600, and 2,000 pounds. And 3 gasket widths, a 1/32, a 1/16, and a 1/8 gasket. Now you have to put 2,500 psi, 3,600 psi, and 4,800 psi on these gaskets in order to seal up to 300 pounds and so forth. Now, using that formula on the previous page, what you come up with for a 32nd inch gasket is 31 foot-pounds. For a 16th inch, 45 foot-pounds. For an 1/8 inch, 60 inch-pounds. And you can see it just goes up as you get thicker, and as the pressure increases, they increase as well. Pretty much straightforward stuff. Took me about 20 minutes to calculate all this out, but my God, it took me almost 2 days to make the slide. When I was installing meters or supervising the installation of meters, I can't tell you how many times we had to start all over again, because it just seems that people didn't get it, that the torquing sequence has to be done a certain way. And also you do have to lubricate all the threads. That's important, because you can bind up a thread if the nut and the bolt just get onto a metal on metal surface, and then your torque calculation is out the window. So I'd always have to, be particular cognizant during that portion of it when they're getting the meter lined up, getting the bolts in, getting the screws on, and snugging them up. Now, snugging them up, you can snug them up by hand. It takes a little bit of work, I admit, but you can snug it up by hand. Then you start to do the rounds. Now, round 1 of torquing is done at 25% of the final torque value, and you do the alternating torque, 1 to 2, 3 to 4, 5 to 6. But you do 1 to 2 on the upstream flange, then you do 1 to 2 on the downstream flange. Then you go to 3 to 4 upstream and 3 to 4 downstream. That's the part that a lot of people miss. You torque up one side of the meter, and then you torque the other side. You're loosening or stretching the other side. Torquing has to be a sequential and equal process, trying to keep it as equal as possible in order to get it right. Well, I've said enough about torquing, so now let's move on to bonding. As we said before, the fluid contact rings serve really one purpose, and that is to complete the measuring circuit from the electrode through the flow stream to the meter body. Now, when you're using plastic pipes, and I don't care what meter you're using, I don't really care whose meter you're using, you have to have 2 fluid contact rings on both ends of the pipe, and they have to be bonded to the meter body. And I'm going to say this because it's going to be repeated over and over again: never, never, ever spike the meter body. And what that means is never take one of these wires, or any wire, from the meter body at any point on the meter body, drive a rod into Mother Earth, and then connect it to Mother Earth. Real simple explanation, and in later seminars we're going to cover that in troubleshooting and what did I do wrong to make my meter all black on the inside. Is if you take a lightning strike somewhere and it can't find Earth anywhere else, it surely will find Earth through your meter and every piece of electronics along the way. When you're bonding metal pipes, it's kind of hard for people to understand that you have to bond all the metal parts to the meter body. The fluid contact ring has to be electrically bonded to the meter body, and the connecting pipes have to be bonded to the meter body, so that all the metal components that would come into contact with the meter and the fluid stream are at the same potential. It's kind of a simple concept. Now, I'm showing a cute diagram here where we have a flange from a pipe and a flange from a pipe and a meter with a fluid contact ring. If you have multiple flanges, say through a valve, you have to bond them too, because if you go 6 inches upstream and then you have some rubber gaskets and a valve and rubber gaskets, you're going to have the same situation. It will get down through that flow stream and it will offset your electrode signal. And the meter is too dumb to realize that it's an offset induced by some potential on the pipe or some stray voltage in the flow stream. The meter doesn't know the difference, and it will register it as flow. This is one of my favorite scenarios, is where you have flange adapters. Now, flange adapters are bolted on, and there's a coating on the pipe, and there's rubber gaskets on it, and when I was installing, I've never seen a flange adapter that was an integral electrical part of the pipe itself. It's not meant to be. It's meant to adapt the pipe to another flange. What you're seeing here is a recommendation that you weld studs on. And somebody says, what? Weld studs on? It's an electromagnetic flow meter. We need positive electrical contact. Grinding down the surface and holding it on with a clamp is not going to work. It will work for a couple of months, and then you're going to be down in that mud hole cleaning it up, using goo on there to keep it clean. That doesn't work. 40 years in the business, I've seen a lot of people try a lot of things. There's only one tried and true way. You weld a stud onto the pipe and you screw or thread that stud, and you screw your connector onto it and bond the pipe to the meter flange, the fluid contact ring to the meter flange. All the metal parts are at the same potential. And the flange adapter, we really don't care, because it's going to be in contact with nothing for all intents and purposes. Now, once again, I'm going to stress, do not spike the meter to Mother Earth. That is a lightning strike dissipation waiting to happen. Okay, this is one of my favorite slides where we reinforce how to assemble any meter. First, you got your upstream pipe work. Then you want your fluid contact ring in there. Then you put your electromagnetic flow meter in there. Notice the little noisy signal there. Then we put the downstream fluid contact ring in. Then we put the downstream pipe work in. Okay, so now we got it. By the way, what's missing here are the gaskets. I left them out. It's just too much work. Now we want to equalize the potential. So we're going to take the fluid contact rings, and we're going to put them in contact with the meter body. Electrode signals are okay, but we're going to cross bond too. Why are we going to do that? It's belt and suspenders, just to make sure. That's a nice slide. We're going to look at some case studies here, and this is the first one, and the complaint here was that they were ripping gaskets and tearing the liner. This was a relatively large meter, and as you can see there, they are in fact tearing the gaskets, and you'll see in a minute that they were ripping the liner. Pretty sure the gasket wasn't properly fitted, but that's secondary to the fact that the meter is hanging on one end in midair when he's torquing, and he's putting an incredible amount of torque on there. I think we estimated that they were putting about 400 foot-pounds of torque on there. I don't know what the breakaway setting was on there, but the maximum recommended torque for that particular meter with that particular flange, the maximum would be 170 foot-pounds. They did, in fact, kind of destroy the liner on this meter, but this is not a proper method for torquing. Now, this is another example of torquing going wrong. This was a large meter, and you can see that the complaint here was that our weld cracked. They called it a manufacturing defect. Now, we took it as a manufacturing defect, but the reality of it is welds do not crack and miss chunks. You can see in the photograph on the left, that's a close-up of the crack. You'll see chunks of the actual weld missing, and that's due to cantilever stress. If you've ever been around one of these things, when they do break, you do kind of, take up some shrapnel. There's a case of improper installation for a slurry. Now, when we first took this case, there was a problem, was it was getting erratic readings and getting a lot of noise errors. And the original explanation of what was going on is that it was a slurry, the flow was upward, and everything was just tight and dandy. But as you can see, when we got into the nitty-gritty of the case, the flow was downward. It was a very thick slurry, and the noise was due to what you can call gurgling, just chunks of slurry material falling through the meter and then air gaps in between. Of course, you're just going to have flow, no flow, noise error. It's just not going to be consistent. And the resolution here was to reposition the meter on the upstream side or the upflow side. This is one of our all-time favors. It looks really nice. I mean, this is a beautiful installation. It's nicely laid out, and you know, things are all lined up and painted pretty, and it's just a wonderful installation. The only problem is the meter on the top talks to the meter on the bottom, and the meter on the bottom talks to the meter on the top. When one meter is not flowing, it's getting flow when the other meter is flowing, and vice versa. There's a specification in the manual, these are water masters, that they had to be a minimum of 2.7 feet apart. Now you have to remember that the coils are powered depending on what's going through them. The power goes up and down. It's not a fixed voltage. There's an automatic gain control in there. So we say 2.7 feet minimum, and I always say get them as far away from each other as possible, just so you don't talk to each other. The resolution here was he had to move one of the meters. This is another interesting installation of convenience. And here the meter in the center of the photograph there is mounted on its side. The reason it was mounted on its side was, as you see, the wire comes out and goes up. He said, well, I couldn't get the wire out of it because the pipe is mounted on the wall. The simple solution here for him was to take the meter out, mount it so that the wires are facing you and the head is at the 12 o'clock position, and wire it that way. If you worry about the flow arrow on a meter, all of our meters and every meter on the market is bidirectional. You can go into the software and change the way it reads, plus or minus, left or right. Doesn't matter. Just put it in so it fits. You can wire it, you can read it, and then we'll work it out in software. And later seminars, we'll get into the commissioning and programming of meters and show you how that's done. So it's like 5 or 6 button pushes. Now you remember earlier with the T and the disturbances and the elbows that had come in at different axes, and well, you see a very large meter here where it became basically an operator's nightmare, because it has flow coming out of a T. It can come from either direction, as I understand. That's kind of bizarre to me, but that's the way it works. And it discharges into an elbow going out. Clearly there's not sufficient straight run. You also have an access port, you have an injection port, and a pressure port. This poor operator just had bad flow data at the wazoo, and there really wasn't a whole lot we can do, and there's not a whole lot he can do, because as you can see, you just don't get in there and take a welding torch and start cutting pipe. This should have been caught at the engineering stage, and somebody should have really thought this one over a little more carefully. The best we could do for this operation was increase his dampening to 60 seconds, which is I mean, to get a reading out of it, 5 times 60 is 300 seconds before you get a stable reading out of it. And that's the best we could do. Noise filtering, of course, really isn't going to help, because this is a pure turbulence problem. Once again, a great looking installation, but totally unfunctional. Unfunctional from the point of view that the meter is entered from a T, from a large pipe, as a matter of fact, which is causing incredible turbulence going into that T. And there's a short run downstream to a motorized valve. It's a gate valve that goes into an elbow. But the cream on the coffee here is the injection port at the top of the T. I believe they were injecting hypochlorite, which wasn't well stirred into the mix and caused conductivity differentials on both sides of the meter. I honestly don't know what the resolution to this problem was, but again, we can only try and dampen it as much as we can. I'm not sure if this one even got off the ground. This is a process master. I believe it's a water master. It could be a process master in the H1 enclosure. Nonetheless, it's a mag meter, and you'll see on the inlet a big motorized valve. Yikes. And then there's a manual valve in front of that. And then it goes right into an elbow, which is connected to a T, which comes from another meter doing the same thing. I honestly don't know how they thought this was going to work, but as you can see, it did work because they didn't even wire it up. This was a picture. There were multiple sites like this. I think, and this is only me thinking, the recommendation is to move that meter on the other side of all that valving and stuff and see if you can get straight run coming into the meter, as opposed to leaving the meter in its current position. And I think that's the way we ultimately got this thing to work. It's another installation of convenience. This is a hygienic master. You'll notice that the lines are insulated, and that's because they're running a cold fluid through there, which, of course, we all know generates condensate. The meter is mounted upside down, which puts the electrode, the grounding electrode, at the top of the meter. Well, that didn't work too well for them. It also, again, condensate comes down through the meter and into the transmitter. The other problem we had with this, you notice that the display is upright. Well, the display can only be rotated 90 degrees, and after that you start ripping the cable out of the control electronics to the display electronics. The solution here was to put a remote sensor in and mount the transmitter on the wall instead of having an integral transmitter. Again, this should have been thought out before they installed it rather than just install it any way it fits. This is an absolute marvel of plumbing. You'll see a ball valve at the top and ball valves to the left and right going into a T, coming out of elbows, which I guess are on the right plane when you think about it. But this is where I was talking about bonding. Now, they got the meter bonded to the meter body, and a lot of our field techs say, hey, well, that's good. But if you take a potential measurement from, say, the left elbow to the meter body, I'm pretty sure you're going to get a difference. Not to mention the fact, and that's just an electrical difference, you're going to have all kinds of turbulence running up through that meter, which is what they had. They wanted to meter the flow from two sides into a common line, and they wanted to be able to isolate the meter completely. They did that, but the meter didn't work well. And again, this was a crank the damping up and take what you get as best as you can. And by the way, they did have to bond everything together. So we've come to the end of all the case studies, and now we're at the part where it's near and dear to my heart. And in every case that I take, I usually end up asking the question, do you have documentation? And a lot of people say, well, I've got this 5x7 thing with 40 pages in it. And that's if you do get that and nobody throws it away with the box. That's a kind of a startup manual, which isn't really a startup manual. Companies don't print a lot of documentation these days. Why? Because it costs money and people throw it away. And anything that costs is going to be rolled into the price of the meter, so to reduce costs, they reduce things that people are just going to throw away anyway. Along comes the internet, and everything that we know and have that's available about this meter is on the internet. It's very simple to find, and a lot of people say, I've looked for hours online, couldn't find it. It's simple. You type ABB.com and you select the new ABB. Always select the new. Why not get new? It takes you to this page that has everything there is to know about ABB products. You go to measurement and analytics, and then you start looking for electromagnetic flow meters and measuring devices. Then you find your meter. It's either a water meter or a process meter, at least in this presentation. Everything is downloadable in PDF, and you have software that is free and available is on these websites. A lot of times people want us to email us manuals. A lot of times I spent emailing manuals only to have them rejected by your servers because a lot of servers won't take the load. Manuals sometimes can be as much as 12 megabytes each. So it's better, this is a kind of an FTP transfer, it's better that you go up, find your manual, and download it. Now, we also have YouTube sites that show you how to do this. We'll get to that in a minute. But this is the basic method of finding our documentation online. You don't have to use Google. You can use Yahoo or Safari or any other search engine that's out there. ABB.com is a global site. So you're going to find every product that we make that is global out there, but there are some products that we only make in the United States, and they're mounted up on ABB Wind. So if you don't find it on ABB Global, then you find it on Wind. I didn't make up the rules, I just follow them. I don't know why we have two different sites, but that's just the way they run it. Now also ABB Win, which you see, it's abb.com, InfoZone, Newsletter, HTM. There's a big one for you. You also have the rep locator. If you want to talk to a rep, get a quote, pricing, availability, replacement part, return something for repair, return something for warranty, you have to talk to our local reps, and they generate the return authorizations. You can find it by just clicking that sales rep locator, plug your zip code into it, and it'll bring up industrial reps, rotometer reps, and municipal reps. But there's a lot of information out there, and this is where I publish my technical bulletins. There are many technical bulletins on mag meters, rotometers, Coriolis meters, pretty much out there. We in the United States, when we write stuff, this is where it gets published. It doesn't get published globally. And I woke up one morning, had a stroke of genius, and I said, let's put some of this stuff out on YouTube. Everybody can find YouTube. You can carry YouTube on your iPhone or your Samsung. And it's just simple ABB Tech, Flowtech support, ABB Flowtech guys. It'll bring you to the YouTube page. We have playlists for Aquamaster, Watermaster, Process Master, Coriolis Master. Anytime I put together a presentation, how to do, I put it up here on YouTube. They're very simple, short, sweet videos. There's no advertising here. I'm not trying to sell you anything. I'm trying to get you up and running. They're point and shoot. You know, we show you what buttons to push and what screens you're going to see. So you might want to go up on this, subscribe to it if you're going to work on these things. You'll be alerted to updates, changes, and new material. Okay? Okay, that pretty much concludes the presentation for installation, and there's always 1,000 questions that have to be asked and answered, and the best way to do that here would be to drop me a line at my email address given below. You can also go up on YouTube and you can drop a line up there, make a comment up there, or you can actually call the help desk. And the help desk is at the end of each YouTube video. You'll see it on there. It's 1-800-435-7365. Hit 3. Hit 3 again. That brings you into the flow group. You'll talk to an operator. They'll want to get some contact information. And what do you want to talk about? What they do is they screen and they triage our calls, because we get quite a few calls. There's only 2 of us handling all of North America, and when the Canadians go on vacation, we pick up their load. But you can always drop me a line. We'll see what we can do to get you a good answer, get you a quick answer, and resolve whatever issue you have. I thank you for listening. If you have any questions, feel free to drop me a line. Look forward to some additional webinars coming up. Hopefully the next one is going to come up in a month. Wiring, how to do it right, that kind of thing. And I hope to see you here again.